All right, hi everybody. So today we're going to be going over something called a telescoping series. And this is one of my personal favorite areas in algebra because they are very fun to work with. They are very quirky and it's just a very fun area in math to do in general. So this is a very special type of series that you may have not heard about before because it doesn't come up often, but when it does, we need to know how to tackle them. Because not every series is going to be arithmetic or geometric, sometimes they can be telescoping. A little background of how this series got its name. So as you can see over here, there's a little picture of a telescope. Because in the old days, the telescopes consisted of a series of concentric tubes such that each tube was a little smaller than the one before it. So you can see we got a little tube here that fits into this bigger one, that fits into this bigger one, so on and so forth. And the thing about these telescopes is that these tubes would collapse one inside the next to be reduced to a single tube. So you can imagine if we were to collapse this thing, this small tube would basically go into this one, and this one would go into this one, and it would just keep going until in the end, you can imagine we basically just have a single tube. And that's basically the same idea for the actual telescoping series. So basically what's going to happen is a lot of terms in the series is actually going to end up collapsing. And you're going to see how that looks like in just a few minutes. But basically what that means is that everything in the middle is going to go away. So what does that mean? Let's take a look. So enough talk about the telescope, let's go into the actual telescoping series. So, what is it? Well, in a telescoping series, many of the terms in the series cancel with other terms in the series. So, there's a lot of cancellation going on in a way that greatly simplifies evaluating the series. Okay, so basically what's going on is in a telescoping series, there's going to be a lot of cancellation. So you might see a series that looks kind of daunting or kind of big, and it looks like there's a lot going on, but really, with some insight, we're going to see that there's actually not a whole lot going on because things are going to cancel. And this sounds very vague right now, I understand. You're going to get a lot more of a better idea of what it's like in the problems that follow, but for now, I want us to just focus on 3 very common setups for a telescoping series. So first, we can have something involving sums and differences. So what that means is we can have a plus term, which is going to cancel with a minus term. So these would go away. A plus term is going to cancel with a minus term. A plus term is going to cancel with a minus term, so on and so forth for the whole series. So that's the first common setup, and I would say this one is actually probably the most common setup. A setup that is not as common, but still just as important, is the multiplying fractions setup. So basically what's going on is this term would cancel with this term. This term, a different term, is going to cancel with this term. So that's why I've highlighted it a different color. And then this term, you can imagine if this series keeps going on, basically this green term would cancel with a green term somewhere later down in the series. And this would just keep going. And then the final setup would look something like number 3. So basically we have a square root maybe in the denominator. So in order to get rid of that and to help us work with something easier, we're going to have to do what's called rationalizing the denominator. So basically that would just mean multiplying the top and bottom by, instead of b plus the square root of c, you're going to be multiplying by b minus the square root of c. So you're just going to be changing the sign. And this very important thing, which has a name, so basically instead of b plus square root of c, we have b minus square root of c that we're going to be multiplying by. This is called the conjugate. So when we say we're multiplying by the conjugate, that's what we mean. Basically, we take the term in the denominator and we just change the sign to a minus. So that's just something I want you to keep in the back of your mind. It might sound confusing right now, but as you can see, we have an example problem coming up. Once we see those, I think you'll totally understand what we're talking about here. So just keep this in the back of your mind as we go on to problem number 1. So this is what telescoping series is useful for. In our problem, we are told to evaluate this giant sum. So we have 998 minus 996 plus 996 minus 994 plus 994 minus 992. You get the idea. It's going to keep going all the way until plus 278 minus 276. Now, I'm going to start off by showing you not necessarily the wrong way, but I guess we could say the inefficient way. So let's write that out. I'm going to show you the inefficient way on purpose to show you just how powerful the telescoping method is when we compare it to this one. So inefficient method So maybe some of us noticed that every term within the brackets would sum up to the number 2. Right? All of these terms equals 2. So we would just sum everything like this. And this is fine. This is not wrong, but I think the big question that we have to ask ourselves is, well, how many 2's are there? So we can count, here's the first 2, second 2, the third 2, but then it's not so obvious, at least for me, right away, how many 2's are there? How many 2's are we summing up here? So we're going to have to spend a bit more time to actually count the number of 2's, and it's totally possible. So you can do that if you want. But I would not recommend this way because we have a faster method. So let's take a look at what telescoping allows us to do. So compare the two methods and decide for yourself which one you think is better. Inefficient versus telescoping. So the whole point of telescoping is that we can rearrange terms in a way that will help us. So what do I mean by that? Let's take this 998 term and let's just leave it alone for now, okay? Now what we're going to do is this time we're going to put the brackets, okay? We still have our negative 996, remember? This time I'm going to pair it up smartly. I'm going to pair it up with a positive 996, and I think you see where this is going. Why would I do that? Well, that's because negative 996 plus 996 is a very special number in math. What's this? I'm pairing up the negative 994 with the positive 994. And this is going to continue. So that negative 992 would be paired up with a positive 992 somewhere later down the road. That's going to show up. And let's see. So this sum is going to continue all the way until, so I can't squeeze it. So I'm just going to continue it over here. Let's put a little dot, dot, dot. So there was a negative 278 term paired up with a positive 278. And then our final term is negative 276 because there is no positive 276 term to pair up with it. Okay, so now here is the magic. Negative 996 plus 996 equals 0. A very important number. 0 just means nothing. So this is going away. That's 0. Everything is 0, actually, including this term, except for the first term and the last term. So I think you can understand the telescope analogy a bit more. Basically, this whole middle portion just collapses. And in the end, we're just left with the ends. And I think we can agree that it's much easier to do 998 minus 276 than it is to sum up a bunch of 2's when we don't even know how many 2's there are in the first place. This means our final answer is just 998 minus 276, which we can even do in our head since that's not so bad, and it ends up being 722. So that was the telescoping method in action. I hope we can agree that this method is very efficient and it saves us a lot of time. So this kind of problem, I would classify it as setup number 1, this one over here, because of the plus minus cancellation that I was talking about earlier, which takes place over here. So yes, I think I love this way so much more. Telescoping is the way to go instead of this inefficient method. So to be able to recognize this setup as a telescoping problem just requires a bit of practice. So over here you can see we sort of had to change how we viewed the terms being paired up, because in the problem they're given like this, but we sort of viewed it more like this. So you can see the commutative property is playing a very big role in this type of problem. So basically, the commutative property is a fundamental property in math that basically tells us it doesn't matter the order in which we add or subtract terms up. So we don't have to add it like this. We can keep the 998 and then pair everything up because we like 0. Anyways, now that you've seen it in action, I think you like that a lot more. You can appreciate the power of telescoping. Correct? That was question number 1. Let's get to question number 2. So, I told you about 3 common setups, and we're going to be addressing each single one. So if the first setup was the sums and differences, well, you might be able to guess what this one is. So we have to multiply a bunch of these fractions. Now, there's a lot of them, and as I said before, I'm not going to cover the inefficient method this time because we only care about the telescoping, but the inefficient way would be, because it's just multiplying fractions, you can multiply every single denominator, so 3 times 4 times 5 times 6, blah, 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 all the way to 49 times 50, and then, put that over all the denominators multiplied, so 1 times 2 times 3 times 4, all the way to times 47 times 48. As I said, you could do that, but I wouldn't recommend it. Why would we bother with this method when we have the telescoping method instead? So, let's do that. Because what I see, and I hope this stands out to you, is, when you take the number 3 and you divide it by 3, you get 1. Multiplying by 1 is basically not changing anything. This means these two cancel with each other. We see a 4 here, it will cancel with this 4. This 5 will imagine there's a 5 here, so it's going to continue. This 6 will cancel with the 6 later down the line. And this will keep on going until when? So that's the big question in telescoping. Until when? How many terms do we keep? So if you're ever confused on how many terms you have left, what I do is I just make a simple chart. So over here, let's call this the top numbers. That's really the numerators, but numerators is too long, so we're just going to call it top. And then this is the bottom numbers, also known as the denominators. So on the top, what do we have? We have the numbers 3, 4, 5, 6, 7, 8, so on, until 49 and 50. And you know what? Let's write the last 3 out, and you'll see why in just a second. 48, 49, 50. Okay, and then on the bottom, we have the numbers 1, 2, 3, 4, 5. This will continue all the way to 46, 47, and 48. Now we know if we have the same number on the top and on the bottom, cancellation occurs. So let's see what we have. So on the top, we have the numbers 3 through 48, and then we have 49 and 50. On the bottom, we have the numbers 1 and 2, as well as the numbers, here it is, 3 through 48. So basically, this 3 goes with this 3. This 4 goes with this 4. This 5 goes with this 5. This 48 goes with this 48. So, in the end, what are we left with? What are the most important numbers here? Well, that would be, and let's remember that 49 and 50 are on the top. This means the final answer is going to be 49 times 50 over 1 times 2, because those are the only 2 terms left on the bottom. Remember, the numbers 3 through 48, they all go away. And I think we can agree this is definitely a lot easier than just multiplying everything through at the start. Because this one is a lot easier to calculate. This ends up being, and I've already done it to the side, 1,225. Let's make it yellow. There we go. Okay, so another example of how telescoping saves us a lot of time. Let's get going to question 3. So if question 1 used the sums and differences setup, question 2 used the, multiplying fraction setup, sorry. Then question 3, you might guess, is going to use the rationalizing denominators. And just a quick tip for rationalizing denominators, basically whenever you see a square root in the denominator, right? So this like ugly, really ugly square root, it's time to rationalize. And we rationalized the denominator, as I said before, by multiplying by the conjugate. So I think you know the drill by now. We are going to be telescoping. So let's rationalize this series. So to find out what this is equal to, we're going to be evaluating each individual one. And because I'm not lazy, I'm just trying to be more efficient, I'm just going to copy and paste it and get to work. So to rationalize this expression, you're going to multiply by the conjugate. As I said before, the conjugate is just take whatever's on the denominator, and just switch the signs. So there we go. It's not too complicated. Just change that plus to a minus. And then you're going to multiply these two fractions as you normally would for two fractions. So top numbers get multiplied together. So 1 times 3 root 2 minus 4. That doesn't change. That's still 3 root 2 minus 4. And then over here, we have 3 root 2 plus 4 times 3 root 2 minus 4. We can continue this. So the top has not changed. And I think by now, you all know how to multiply an expression like this. That ends up being 3 times the square root of 2 squared, because we have 2 copies, minus 4 squared. Because the 2 terms in the middle cancel. So this negative 4 times 3 root 2 ends up being negative 12 root 2. But then we're adding plus 4 times 3 root 2. That's a plus 12 root 2 minus 12 root 2 plus 12 root 2. Oh, once again, that's 0. So those go away. In the end, we're just left with these 2 terms. And let's simplify the bottom a bit. So 3 root 2 squared. So that's going to be 3 squared times the square root of 2 squared. So that's going to be 9 times 2, which is 18. So let's write that out, 9 times 2, which is 18 minus 16. So in the end, that's a lot of work just to show this, but I want to go slowly. 3 root 2 minus 4 over 18 minus 16 is 2. Okay, now you might be wondering, how did that help? Because, we still have a square root term. This time it's on top. And then now we have a 2 in the denominator. Well, to that I say just be patient, because that was only one term, remember. We have 5 terms here, so yes, we're going to have to do this 5 times. Rationalize this by taking your term in the denominator and just switching the signs. So I'm going to be going through this a little faster. This is 4 squared minus the square root of 14 squared Four squared is 16. Square root of 14 squared is 14. 16 minus 14 is 2. Interesting. So we got a 2 here and a 2 here. You know that fractions with the same denominator can be combined, right? Interesting. Let's see if this fraction can be rationalized to something over 2 as well. Because if it can, then we know we are heading on the right path. Because you can always look ahead in your solution. If we were to combine these two fractions, this negative 4 would cancel with this positive 4 on top. So there's a positive sign there. So these two terms would go away. And already I see a minus square root of 14 here. So maybe it can go away with this positive square root of 14. So that's another tip I have for you. If you can look ahead in your solution and see that you're going the right way, well then keep going. Finish strong. Don't give up halfway. And keep doing what worked. So if it worked the first time, well, let's do it again. Square root of 14 minus 2 root 3. It's the same logic. Square root of 14 squared minus 2 root 3 squared. Now, the square root of 14 squared is just 14, and 2 root 3 squared is 4 times 3, which is 12. 14 minus 12. Hope you're not surprised by that, but that's also 2. And now we see, yes, if we were to combine all three fractions, negative 4 goes with positive 4, negative square root of 14 goes away with positive square root of 14. Let's do it 2 more times and then we'll be done. And then hopefully we can get a simple answer. So I obviously, as usual, keep underestimating how much space I'm going to need. So right away, I'm going to add a page. The conjugate is 2 root 3 minus the square root of 10 over 2 root 3 squared, which we already know is 12 from before, minus the square root of 10 squared, which is 10. Surprise, surprise, this ends up being 2 root 3 minus the square root of 10 over, that was not a straight line, 2. And the final term, this one over here, sorry, I don't like how that looks. It's a little squiggly. So this ends up being the square root of 10 minus 2 root 2 over the square root of 10 squared minus 2 root 2 squared. square root of 10 squared is 10. 2 root 2 squared is 4 times 2, which is 8. So this is also over 2. So in the end, let's see, what do we have? This original expression that we had at the start is actually equivalent to, let's take all of these and just put them here. At the end, line them up nicely. You can see my best friend is the copy and paste button. Okay, this is kind of annoying, but there's like one term that just doesn't fit. So I'm going to have to put it here. Now, you know that all of this, because they have the same denominators, so they're all over 2, this can be combined to one giant fraction over 2. And then we just write out what we see in the numerator. Which would be all of this, and it looks scary right now, but I think if you remember from question 1, what we have is a bunch of terms that can go away with each other. So this -4 goes away with this +4. That's a 0, that's a 0, that's a 0. 3 root 2 minus 2 root 2 is just the square root of 2. All of that over 2. So this ends up being the final answer. Okay, square root of 2 over 2. That was pretty nice. So far we've seen one technique for each problem. So one common setup for each problem. Now let's get into something a bit more interesting. Something not as obvious. So this time we are told to evaluate this giant expression over here. You might be a little confused because there are no sums and differences, so there's no negative signs right now. It's not like there's a 4 in the numerator to cancel it with, right? In fact, there's 2 4s in the denominator, and there's no square roots, so you're probably like, probably can't rationalize that, so what do we do? That's a very good question. And over here, I have a little bullet point which will actually make this very easy for us. There's a little identity here that says 1 over k times k plus 1 for some number k is equal to this. So basically the fraction can be split up. And you can see all of our fractions in this problem are of this form. You take k to be any random number. Let's say you thought of like 3. And then k plus 1 ends up being 4. Well, then that's this term over here. So if your k was like 99, then k plus 1 would be 100. Well, that's this term over here. So basically, every term has this general form. That means we can actually rewrite them like this. We just have to be careful. So I'm going to start with this one. So 1 over 1 times 2. Ask yourself, what is your k? Here our k would be equal to 1. This means that fraction can be rewritten as, well, 1 over 1 minus 1 over 2. One over 2 times 3, so the next fraction in the sum. This time our k is 2, so we can rewrite that as 1 over 2 minus 1 over 3. And you can verify for yourself that this 1 over 2 minus 1 over 3 actually does equal this. The next term would be 1 over 3 minus 1 over 4, and I think you see where this is going, because it actually is a sums and differences problem just in disguise. And this would keep continuing until, let's move this all over to the left, just to give us a bit of space. This continues all the way to plus, well, I'm going to write the term before it, just to make it a bit more clear. Plus 1 over 99 minus 1 over 100. And now, once again, this is my favorite part of telescoping, is just writing these little, like little ticks, these little cancellations, because all of these go away. Because negative 1 over 2 plus 1 over 2 is 0, negative 1 over 3 plus 1 over 3 is 0, so on and so forth. In the end, we are left with just, that's not black, we are left with just 2 terms, the first and the last. And this is a lot easier to work with because 1 minus 1 over 100 is just equal to 99 over 100. So this is our final answer for this problem. Now, keep in mind that we were only able to do this problem because we were given this useful tip. But let's say we were not given that. How would we find something like this? Well, that's a topic for another day. I'm glad you asked that question, but that is a topic for another day. So because there is a method to actually find this, and it's called partial fraction decomposition. So fancy, pretty fancy term. That's just annoying. How it doesn't fit, come on. Decomposition, okay, something like that. Okay, I think that's good. Decomposition, there we go. That's good enough. So yeah, I'm gonna make a video on that some other day as well, but it's a pretty powerful technique that you would also have to know to get this problem. But for now, don't worry too much about this partial fraction decomposition. I just want to save us some time and just show the telescoping in action. So that's why I gave it to you right now. Okay, so I'm being a little generous. I gave you this. But if you're wondering how to get it on your own, again, sometime in the future, we're going to be covering that. Let's get on to our final problem of the night. Again, I give you another tip just to make things a bit quicker. But here's your final question. It's a monster problem. We got this giant fraction, this giant scary looking fraction to evaluate. 100 squared minus 99 squared times 100 squared minus 98 squared. Oh my gosh, and I just realized, sorry about that, guys. It's very important. So that square is not outside the bracket. It's like this. So the question document might be a little messed up, but this is what I mean. Times 100 squared minus 97 squared. And it just continues, to 100 squared minus 1 squared. And then, that's not all. We have to divide by, all of that. So pretty scary. I think you know the drill by now though. We are not going to find out what 100 squared is and then subtract 99 squared. We are not going to find out what 98 squared is, right? And then subtract it from 100 squared. No, that's not what we're doing. We need to use the telescoping series, but right now it's not really in a useful form. So that's why I chose this as the last problem. You're going to have to use in math everything you know. And right now this question is basically begging us to use difference of squares, which is such an important identity that you must know. But basically, difference of squares says for any number of this form, a squared minus b squared. So that's perfect because our problem is literally of this form. We have many terms of that form. Well, then you can break that down into a plus b times a minus b. And if that doesn't look like it will help right now, just you wait. Let's use difference of squares on every single term in this problem. Yes, every single term, starting with 100 squared minus 99 squared. So this one over here can be rewritten as 100 plus 99 times 100 minus 99. Same thing for 100 squared minus 98 squared. That's equal to 100 minus, well, actually let's do plus 98 times 100 minus 98. The third term, I'm just going to do all the terms that we can see right now, can be rewritten as this. And this would continue to 100 plus 1 times 100 minus 1. So that's 100 squared minus 1 squared, just written in the useful difference of squares form. Okay, now it's a little, I know this looks a little confusing, but we have to like divide all of that. This looks really weird, I know. I'm sorry, it's just a space, it's just so cramped. Anyways, 99 squared minus 98 squared. Let's rewrite that into the difference of squares form. So that's 99 plus 98 times 99 minus 98. And do this for every single term. 99 squared minus 97 is the same as 99 plus 97 times 99 minus 97. 99 squared minus 96 squared is 99 plus 96 times 99 minus 96. This is going to continue until 99 plus 1 times 99 minus 1. So, again, I think I'm going to give myself some more real estate. Now, let's see. Instead of working with all of these sums, we do know that we can actually simplify the terms in the sums because 100 plus 99 is just 199. 100 minus 99 is just 1. So let's rewrite all of these actually as a single number. So what we have is our first term, 199 times 1 times 198 times 2 times 197 times 3. This will continue all the way to, we see 101 times 99. And then over here on the bottom, we're going to do the same thing. So 99 plus 98 ends up being 197. 99 minus 98 is 1. 99 plus 97 is 196. 99 minus 97 is 2. 99 plus 96 is 195. 99 minus 96 is 3. This will continue to 99 plus 1 is 100. And 99 minus 1 is 98. So you can see now it looks like we are in the setup number 2, the one where we have multiplying fractions, because basically whenever you see the same number on the top and the bottom, those can go away. So that's what we mean by a fraction of 1. 3 over 3 is 1. 2 over 2 is 1. And check this out. 197 over 197 is 1 as well. So let's stay organized. Now you can do the chart method that I did before just to keep track of what you have on the top and on the bottom. But what I'm going to do is just first we're going to rewrite this. Let's go from smallest to biggest. So basically I'm just keeping track of 1, 2, 3. This keeps going, so we have everything 4, 5, 6 all the way up to 99. So that's 98 times 99. We do not have 100, but we do have 101. And we have 102. In fact, we have everything until 197 times 198 times 199. And then on the bottom, you can see we have a 1 times 2 times 3 all the way to 98. But this time we're going to skip 99 and then we're going to start from 100 times 101, and this will continue until 195 times 196 times 197. And now we see what can go away. 1 goes with 1, 2 goes with 2, 3 goes with 3, so basically the first 98 numbers all go away. 99 is on the top, but it is not on the bottom, so that's going to stay. 100 is on the bottom, but it is not on the top, so that's going to stay. 101 goes with 101. 102 is going to go with 102, somewhere over there. And basically all the numbers until 197 will go away. Now, this 198 and 199 on top has no 198 and 199 on the bottom to pair itself up with. So that just stays there. This means we have 3 terms on top. We have 99, 198, and 199. And then on the bottom, we have the number 100. And you can leave your answer like this, but this actually ends up also, I'll take this as an answer as well, because it's the same thing. It's actually a not so nice decimal, but it's this, 39,007.98. So, I hope you enjoyed that one, but I hope you see how we have to use everything we know in algebra. We cannot forget our difference of squares identity, and this problem, just based on the setup, was begging us to use difference of squares. But once we did the difference of squares, we were able to get it into a nice telescoping form. Amazing. And that concludes today's lesson on telescoping. So, with that all out of the way, I think I've showed you enough methods to be able to answer the homework questions that you are given. So, your homework, you have 3 questions. Looks something like this. So, question 1, I think a lot of you can recognize. It's sort of similar to the question 1 that we did in class today, just a little bit different because now things have shifted a bit. So They're not right next to each other, but this negative 845 is going to cancel with this 845. This negative 843 is going to cancel with this 843. So just keep track of what terms at the start you have and what terms at the end you have. So for this, I would probably use the chart method that I showed you before, just to keep track of everything. And for questions 2 and 3, well, you got square roots, so you know what to do. Rationalize them, and you should be good. So that concludes the telescoping lecture. This was just a little introduction, and I hope you have fun with it. So these 3 questions, their solutions will be posted in the solutions document. So make sure to check those out. So I hope you had fun with telescoping. As I said before, it is quite a fun unit. It's fun to just cross everything out. Yeah. Don't be afraid to just cross them all out as hard as you want. So I hope you saw how telescoping works. Always stay organized. I think that's one of my biggest tips I can give you in telescoping. You always gotta keep track what goes away and what stays. But anyways, with that being said, this was telescoping. And now that you understand how it got its name, everything in the middle goes away. I think it's time for you, for me to go away and let you solve these problems. So have fun. Thank you for watching, and I'll see you in the next video. Bye.